1,200 kilometers from the nearest settlement, research station Kepler-9 operates in total isolation. Its only lifeline is a single fiber optic cable buried deep in the ice, maintaining a fragile physical link to the outside world. Inside that glass core is Frame 7. It is a single packet of telemetry data, representing the basic unit of information traveling across the data link layer of a network. Before Frame 7 can start its journey, the network has to solve a mechanical problem. Kepler-9's transmitters can push data into the cable at extreme speeds, but the relay station on the other end has a limited processing speed and a finite amount of memory to hold incoming data. If a conveyor belt feeds crates faster than a worker can unload them, the crates pile up and spill. Data networks behave exactly the same way. When a sender transmits data faster than a receiver can process it, the receiver's memory buffer fills to capacity. Any packets arriving after that point have nowhere to go, and they simply vanish. Flow control acts as the brake system for the network. It dictates the pace of transmission, ensuring the volume of data in the pipe never exceeds the receiving hardware's physical capacity to survive it. The absolute simplest pacing method is a protocol called stop and wait. The sender transmits exactly one packet and then pauses completely until the receiver sends back a confirmation message. This timeline maps the physical reality of the link. Pushing the bits onto the wire takes a fraction of a millisecond, but for the signal to physically travel hundreds of kilometers across the ice, and for the acknowledgement to travel all the way back, takes an eternity in computing time. Looking at the efficiency formula overlaid here, the math reveals a severe bottleneck. The transmission time divided by the total round-trip time yields a tiny fraction. The sender is spending the vast majority of its time sitting completely idle, waiting for the speed of light. To eliminate that idle time, networks use the sliding window protocol. Instead of sending one packet and waiting, the sender continuously fills the empty pipe with data. Here, this sequence of numbered slots tracks the transmission limit. The sender launches multiple frames back to back. As the receiver confirms packets have arrived, the window slides forward, allowing new data to enter the link in overlapping succession. Pipelining solves the throughput problem, maximizing transmission speed. But keeping the pipe packed with data creates a new risk. If something damages the physical cable, multiple frames are in flight and vulnerable at the exact same moment. Buried alongside high-voltage conduits, the physical link is exposed to electromagnetic interference. These invisible fields can violently warp a passive signal. Sometimes interference flips a single bit, turning a 0 into a 1. More commonly, a burst of electrical noise corrupts a whole consecutive block of data. If the destination accepts this corrupted pulse, the system records garbage. To combat physical chaos, the network uses error control, specifically a framework known as Automatic Repeat Request, or ARQ. Every ARQ system requires 4 components: a mathematical checksum to detect corruption, explicit feedback messages, sequence numbers to verify each packet, and a countdown timer to automatically trigger a retransmission if a packet vanishes into the ice. Reliability requires an active, continuous dialogue. The sender and receiver must constantly verify the integrity of what survived the journey. Because packets fly continuously in a sliding window, they need sequence numbers. But a packet's header has finite space, meaning the numbers can't count up infinitely. Instead, they count up to a limit and wrap back around to 0, using modulo arithmetic. Go back N ARQ enforces a strict mathematical rule. The sender's window can never be larger than 1 less than the maximum sequence number. This cap ensures the receiver will never confuse a brand new packet with an old wrapped-around retransmission. The flaw in this protocol reveals itself the moment a single frame within a packed pipeline is corrupted in transit. On this schematic, you can see the receiver's blunt defense mechanism. The receiver only accepts data perfectly in order. When it detects a corrupted packet, a gate slams shut. It throws away the damaged frame, and it actively locks out and discards every perfectly healthy frame that arrives after it. To recover, the sender's window snaps backward to the point of failure. It is forced to retransmit the corrupted frame, plus every single healthy packet that was trailing behind it. Go Back N prioritizes cheap, simple hardware on the receiving end. It pays for that simplicity with a massive penalty in wasted bandwidth every time a single error occurs. Selective Repeat ARQ takes the exact opposite approach. It is a precision-engineered alternative built specifically to eliminate the bandwidth waste of Go Back N. First, it cuts the maximum window size in half. This stricter limit safely accommodates packets arriving completely out of order without risking sequence overlap. Looking at this receiver diagram, the mechanical difference is clear. Instead of slamming a gate shut, the receiver uses individual storage drawers to safely capture and buffer the out-of-order healthy packets, isolating the corrupted data by leaving its specific slot empty. The receiver sends a targeted negative acknowledgement. The sender surgically retransmits only the single missing frame. Once it clicks into the empty drawer, the receiver releases the complete set upward to the next layer in perfect numerical sequence. Selective Repeat achieves flawless bandwidth efficiency. It resends only what is broken, requiring complex sorting logic and expensive memory buffers to physically reorder reality. You have a choice: Go Back N's hardware simplicity or Selective Repeat's transmission efficiency. This scatterplot maps link efficiency against implementation complexity. Go Back N requires minimal processing but drops in efficiency on noisy lines. Selective Repeat maximizes throughput but sits at the extreme high end of hardware complexity. Protocol design is an act of calibration. Engineers expertly balance the physical error rate of the environment against the hardware budget of the machines they deploy. These mechanics operate constantly within the infrastructure underneath every action you take online. The transmission control protocol relies on sliding windows to pace every video call and file download. High-level data link control and modern Wi-Fi use selective retransmission to ensure your data survives the constant interference of wireless signals. Frame 7 finally clears the buffer, delivering its ICE core telemetry perfectly intact. Through active pacing and relentless mutual verification, these invisible protocols ensure that the signal across the ICE always arrives exactly as it was sent.